Check, check. Hi students, welcome to the ACE online platform. So as you all know, we are dealing with the ISRO exam. So it is Mission ISRO 2025. So this session is targeted for the electronics and communication engineering students who are preparing for the upcoming ISRO exam. So here I will going to deal with the electromagnetic theory or electromagnetics. See, if you observe the previous papers, as far as this subject is concerned, their objective is very clear, their intentions are very clear. So if you notice the type of the questions are more on the application part of the electromagnetic theory. Instead of, if you observe the syllabus for the electromagnetic theory, as you all know, it starts with the Maxwell's equations, EM wave propagation, waveguides, transmission lines and antennas. So the syllabus is somehow same as a gate syllabus. But remember, so the more questions will be on the applied electromagnetic theory. That means the questions are more on waveguides, transmission lines and antennas. Okay, fine. Because the ISRO organization deals with the antennas, deals with the microwave communication, deals with the wireless communication, deals with the guided waves. So that is the reason why the questions are also in the same manner. Fine. So here in this session, what we are going to do, we are going to take up some previous questions. Through those questions, we will understand what is the level of questions asked, what is the type of questions asked, what is the difficulty level, what is the nature of questions, and I will going to highlight the points which actually you need to remember for your exam. Fine. Okay. So we will directly dive into the questions here. Fine. So here are some of the questions which I have collected. See, here is a question. As I said earlier, the more questions, just I wanted to know. Yes guys. Okay, here is a question. This question is on the transmission lines. A transmission line with a characteristic impedance of 100 ohms is used to match 50 ohm section to 100 ohm section. So that means there is a transmission line is having a characteristic impedance of 100 ohms. I want to match it to the 200 ohms. Yes, 50 ohms. So and 200 ohm section is used. So if the matching is to be done both at 500 megahertz and 1.2 gigahertz, the length of the transmission line can be approximately. See, as you all know, let me elaborate this one. So there is a quarter wavelength matching transformer. So for the quarter wavelength impedance matching transformer, that means if you have a transmission line and you want to connect, you want to match to the load of certain value. So a transmission line with a characteristic impedance of 100 ohms, these are 100 ohms, use it to match, no, not that one. So 100 ohm is used to match. That means between these two things, there is a one line whose characteristic impedance is 100 ohms. This is used to match 50 ohm section to the 200 ohm section. So it is a 50 ohm section. This is other 200 ohm section. So it is a long length transmission lines. We are using one section to connect the two sections. Fine. So obviously this must be a quarter wavelength impedance matching transformer. Why? Because what is the design formula for the quarter wavelength impedance matching transformer? This must be a geometric mean of these two things. That means 100 is equal to square root of 50 into 200. Yes, correct. It is 100. So obviously what it must be? This length must be, what is the section used to match the two transmission lines, or here is a transmission line, it can be load also. So this must be a quarter wavelength. Fine. So indirectly or directly is saying that whatever the section used is a quarter wavelength impedance matching transformer. As you all know, so not only quarter wavelength impedance matching transformer, odd multiples of quarter wavelength impedance matching odd multiples of a quarter wavelength transmission lines also act in a same behavior like a inverter. So the quarter wavelength impedance quarter wavelength transformer, quarter wavelength section of a transmission line is called an inverter. Not only just lambda by 4 length, odd multiples of lambda by 4 length also offer the same behavior. See, the impedance need to be matched at the two frequencies. It is not a single frequency. So if this would have a single frequency, then you can find out its corresponding wavelength and divided by 4. You will get a length. You can find out the single wavelength and you can divide by the 4. You will get a single length. But the matching need to be done at the two frequencies. We are going to find out what is its corresponding wavelength here. Let me turn the page here. I will call that as a lambda 1. So the lambda 1 is equal to C by F. So 3 into 10 to the power of 8 divided by 500 mega. 500 into 10 to the power of 6. So you can check out lambda 1 is equal to 0.6. Okay. And similarly, what is this lambda 2, guys? Lambda 2 is equal to C by F, 3 into 10 to the power of 8 divided by frequency. So 1.2 giga. 1.2 into 10 to the power of 9. So the lambda 2, you can check out, this will be equal to 0.25. So it is 1 by 4, something like that. So if you wanted to match this frequency, the length what is required is lambda 1 by 4. So what is the lambda 1 by 4? 0.6 by 4. This is some 0.15. So here it is lambda 2 by 4. Lambda 2 by 4 is, you can check out, this will be 0.625. This is in the meter, that is also in the meter. These two lengths are not same. But remember, not only just, but the matching need to be done at the two frequencies. So for that, you can keep on multiply this one with 3 lambda 1 by 4 and then 5 lambda 1 by 4, 7 lambda 1 by 4. You can check out 7 lambda 1 by 4 will be equal to 1.05. And if you keep on multiply this one also with the odd multiples, so this is 3 lambda 2 by 4 and 5 lambda 2 by 4, so on up to 17 lambda 2 by 4. At that point, this will be equal to around some 1.06. So around some 1 meter length of a transmission line is if is used, then the matching will be done at the two frequencies. So these calculations you have to do. Okay, guys, there is no other way. So what is the answer here? 1 meter. Option B is answer. You will find the same model in the GATE exam also for the 2 marks, but such a lengthy question asked in the ISRO paper. Fine. So here and there you will find not only theory question, not only formula based question, little bit such a conceptual questions also you will notice in the ISRO paper. Okay, guys. So this is directly a GATE question. It was asked for the 2 marks in the GATE paper with the different values of the frequencies. The same model was used, same model was given in the ISRO paper also. Anyhow, let us proceed further. Here is a one more question. This is related to the waveguide. Yes, guys, are you all with me? Try to answer these questions. Let us make this session more interactive. Okay, here is a question, guys. An air-filled rectangular waveguide R1 is operating at a frequency of 2 gigahertz, and another air-filled rectangular waveguide R2 is operating at 4 gigahertz. The guide wavelength of these waveguides at their respective frequencies are equal. Okay, if the cutoff frequency of R1 is 1 gigahertz, what is the cutoff frequency of the R2 in gigahertz? Okay, guys, see, when it comes to the waveguides, theoretical questions were also noticed in the previous papers. I have not considered the theoretical questions here. So, generally the theoretical question, something like a waveguide is a high pass filter. What is the wavelength inside the waveguide compared to the unbound medium? So, there will be some, and the questions was on the dispersion, the questions was on the inequality for the phase velocity, group velocity and intrinsic velocity. Such a theoretical questions was noticed equally in the ISRO paper. So, as far as the electromagnetic theory is concerned, around some you will find 6 to 8 questions purely for the from the electromagnetic theory. Among that, 2 to 4 questions on theory based, fine, which you can easily handle. Okay, guys. So, here two waveguides are there. For those two waveguides, wavelengths are guided wavelengths are same. So, let me turn the page here. What is the guided wavelength formula? The guided wavelength formula is lambda bar is equal to lambda divided by square root of 1 minus fc by f whole square. It is a high pass filter term. So, this is also can be written as c by f, c divided by f, c divided by f square root of 1 minus fc by f whole square. This is also can be written as c divided by f into square root of 1 minus fc by f whole square. You can bring this f inside, then it will become f square. So, this will become c divided by square root of 1 minus, not 1 minus, f square minus fc square. So, in the for the two waveguides, the guided wavelengths are same. So, let us equate those things. C divided by square root of 1 minus is asking what is the cutoff frequency for the second one. For the first one, operating frequency is 2 gigahertz. It is a 2 giga whole square minus cutoff frequency. For the R1, cutoff frequency is 1 gigahertz. It is a 1 gigahertz whole square. For the second waveguide, C divided by square root of 1 minus, what is the operating frequency? The operating frequency is 4 gigahertz minus, and for the we do not know what is the cutoff frequency for the second waveguide, that is what is asking. So, let me call this as a FC. Take the cross product and perform the squaring on both sides. It will become 4 gigahertz square minus FC square. So, it is 2 gigahertz square minus 1 gigahertz square. Okay. So, it is 4 gigahertz. It is a 16 gigahertz square minus FC square. It is a 4 gigahertz square minus 1 gigahertz square. Okay. So, let me shift this one. It is a simple algebra. It is a simple question. Okay. It is purely formula based question which you can easily handle. So, it is 16 gigahertz square minus FC square. It is 3 gigahertz square. Bring this one here, this one here. It is a 13 gigahertz square which is equal to FC square. Okay, guys. So, what is the FC here? Frequency cannot be negative. So, negative frequency has no meaning. So, it is 13 square root of 13 gigahertz is the answer, is the cutoff frequency for the second waveguide. So, square root of 13 gigahertz. So, what is the answer, guys? Option D is the answer. Okay, fine. Let us proceed further. Let us have one more question. So, here is a question. Yes, this is related to the electromagnetic waves. So, an electromagnetic wave propagating through a lossless medium, lossless insulator with a velocity 1.5 into 10 to the power of 10 centimeter square, centimeter per second. Calculate the electric and magnetic properties of the insulator if its intrinsic impedance is 90 pi. It is a simple and straightforward question, formula based question. So, what is the intrinsic impedance? Eta is equal to square root of mu naught mu r epsilon naught epsilon r, yes, which is equal to 90 pi. This can be written as 120 pi square root of mu naught epsilon r, which is equal to 90 pi. So, square root of mu r by epsilon r 9 by 12. So, it is 3 by 4. Keep this one aside. Similarly, you can even equate it to the velocity formula. 1 divided by square root of mu naught mu r epsilon naught epsilon r, which is equal to, convert this one into the meters, 1.5 into 10 to the power of 10 into 10 to the power of minus 2 meter per second. Okay, guys. So, this can be written as 3 into 10 to the power of 8 divided by square root of mu r epsilon r, which is equal to 1.5 into 10 to the power of 8. You can bring this one there. So, square root of mu r epsilon r is equal to 2. Am I correct? So, you have got a 2 equations here, 2 unknowns. You can find out the mu r and epsilon r. Let me turn the page here. So, you have to read the question properly. You have to do sometimes elimination also, fine, which will save our time. So, what is the square root of mu r by epsilon r? Mu r by epsilon r is 3 by 4. The other one is square root of mu r epsilon r is equal to 2. Correct? I will multiply these two things so that you will going to get mu r value. If I multiply these two things, so the mu r is equal to 3 by 4 into 2. So, which is 3 by 2, which is 1.5. So, check out, do we get the answer just by calculating the mu r? 1.5. Yes, here is a 1.5. So, the mu r value is 1.5, no other option is having such a value. So, you can decide option A as the answer. You no need to find out the epsilon r value. That is how we can save our time from the elimination technique, fine. But for our practice, let us find out the mu r also. So, how do you find out the mu r, guys? I am going to divide this one, this divided by this. So, you are going to get epsilon r is equal to 2 divided by 3 by 4. So, which is 8 by 3. Okay, 9 by 3 is 3, 8 by 3 is less than 3. So, epsilon r is equal to 2.66. So, 2.66, yes, option A is answer. Okay, guys. Yes. Now, observe the next question and try to answer that one. Here is the next one. Here is the next one. Again on the waveguides. Yes. So, it is on the square waveguide. A square waveguide carries TE11 mode, whose axial magnetic field is given by Hz is equal to this entire thing, H naught cos pi x by root 8 cos pi y by root 8 ampere per meter, where waveguide dimensions are in the centimeters. Okay. What is the cutoff frequency of the mode? Okay, fine. See here, guys. Now, you can compare this one with the standard form. TE wave is being supported by the extramagnetic field. Here Ez is 0, Hz is not equal to 0. What is the Hz? Cos into cos, isn't it? So Hz is equal to H naught of z into cos m pi by a into x cos n pi by b into y. You can make a comparison here. So in the place of m you are having a 1. So if you want to rewrite one more step, you can write down H naught of z cos pi by a into x cos pi by b into y. So in the place of a you are having root 8, in the place of b you are having a root 8. A is equal to, this implies by comparing a is equal to b is equal to root 8. Yes. So the root 8, it is the root 8. Then what you can do, root 8 centimeters, obviously. He said centimeters. So is asking what is the cutoff frequency, right? Let me turn the page here. So is he asking the cutoff frequency? Yes. Let me turn the page. What is the cutoff frequency, guys? FC TM11, not TM11, TE11. So you are comparing with the standard form and you are obtaining the dimensions mu naught epsilon naught square root of a square plus b square by a into b. A square and b square are same. Everything is in the centimeters. So square root of 8 into 10 to the power of minus 2 whole square plus square root of 8 into 10 to the power of minus 2 whole square divided by square root of 8 into 10 to the power of minus 2 into square root of 8 into 10 to the power of minus 2. Do these calculations. So which is 3 into 10 to the power of 8 divided by 2 into square root of 8 into 10 to the power of minus 2 into root 2 divided by square root of 8 into square root of 8 into 10 to the power of minus 4. So this will become 3 into 10 to the power of 8 into root 2 divided by 2. Yes, this root and root will go, this is root 8 into 10 to the power of minus 2. So this will become 3 into 10 to the power of 10. So this is root 4 is 2. So it is 1.5 into 10 to the power of 10. This can be written as 15 gigahertz. Somewhere some calculation error. Yes, this one is 4 here. It is 0.75. Yes, correct. So 0.75, this can be written as 7.5 gigahertz. Okay, guys. Yes, let me go back here. 7.5 gigahertz. Option C is answer. See, every word is important. He said centimeters. Okay, clear. Let us proceed further, guys. Here is a one more question. See, so the questions are on the numericals are on the transmission lines, numericals are on the waveguides, numericals on the antenna, the two antenna parameters. Okay, understand. Obviously, so that means he will be asking the questions in the electromagnetic theory, as I said earlier, applied electromagnetic theory. Where do you find the applications of electromagnetic theory? In the transmission lines, antennas, waveguides, and microwave communication, and then fiber optic cables, radars, satellites, advanced communications systems. So from all these topics, questions are there in the ISRO paper. Okay, so you need to focus on those topics. Anyhow, so here is a question, guys. So this is on the antenna parameters. The electric field of a linearly polarized, in the question itself it is mentioned that it is a linearly polarized electromagnetic wave is given by this one, is incident upon a linearly polarized antenna whose electric field polarization expression is given by like this. Find the polarization loss factor. Fine. So suppose there is a, for every antenna there is a state of polarization. Suppose if I say that the state of polarization of certain antenna is circular polarization, so it will respond maximally to the incoming wave which is of circular polarization. If it is horizontally polarized wave, polarized antenna like a Yagi-Uda antenna, okay. So if the incoming wave is also horizontally polarized, then the efficiency is 100%. If the incident one is vertically polarized, then the efficiency is 0%. Okay guys, fine. So obviously one can say that the incident one is linear x oriented, and what this antenna is expecting is linear. So this will respond to this one. So half of the power will be wasted and efficiency will be 50%. That is how you can directly decide, but let us go through the formula here. The formula here is polarization efficiency factor. Polarization efficiency factor is equal to magnitude of AW AA conjugate magnitude square. So AW in the sense it is the unit vector associated with the polarization of the incoming wave. So what is the polarization of the incoming wave is the x cap, and it is a real part, so the conjugate has no meaning. And what is this AA? It is a polarization of the unit vector associated with the antenna state of polarization, which is x cap plus y cap divided by root 2 magnitude square, which is 1 by root 2 magnitude square, which is 1 by 2. So half of the power is wasted. Our efficiency is only 50%, one can say. So what is the answer, guys? Option A is the answer. So the focus on the antenna parameters. When it comes to the antennas, there are, when you make a comparison with the GATE syllabus in the ISRO paper, there are some extra antennas you need to focus. Especially you need to focus on the microwave antennas, parabolic reflectors, E plane T, H plane T, yes, yeah, horn antenna, sorry, not E plane T, H plane T, horn antennas, Yagi-Uda antenna, antenna arrays. So some of the practical microwave antennas you need to focus, you need to learn some formulas related to them. So there are some repeated questions on that. Anyhow guys, let us proceed further. Here is a one more question on the antenna parameter. See, so every year in every paper you will find 1 to 2 questions on the antenna parameters. That is obvious thing. ISRO organization, ISRO satellites are dealing with the antennas, wireless communication, microwave communication. So obviously there will be a use of microwave antennas. So obviously their objective is also very clear. That is how the questions are prepared. That is how the paper is prepared. So the electromagnetic theory combined with the communication will going to play a major role in the selection process of your ISRO paper, ISRO exam. Okay, fine. So an antenna has a radiation resistance of 72 ohms, a loss resistance of 8 ohms, power gain of 16. Calculate its directivity. It's a play of formulas, nothing more than that. Okay, so what are the formulas we know? Power gain is equal to efficiency into directivity. Okay, so what is he asking for the directivity D? So the D is equal to G by eta. What is this eta? A radiation resistance divided by radiation resistance plus RL. So what is the radiation resistance? It is a 72 divided by 72 plus 8. 72 divided by 80. Clear guys? That is the efficiency. Okay, and then you can find out the directivity. So what is the gain here? The gain here is a 16. 16 divided by 72 by 80. So it is 16 into 80 divided by 72. So this is 10 times, this is 9. So the D, it is a 8 tens are 8 nines are. So it is 1 point something. Yes, 1.11. So you check out little bit more than that 16. How much is this, guys? 16 into this one. Just a second. So, how much is this? 16.8 or 17.8. What is the answer? Yes, guys, what is the answer? $16.8, I think. Try to interact with this one. Yes, it is not 16.17.77 or 17.8. So, it is 1.11. So, it is 17.8. Option C is the answer. Okay, guys. Let us proceed further. Here is a question. Again, this question is on the antenna parameters. You have to understand how important antenna parameters are. Yes, 17.6. Anurag, you are correct. So, keep commenting your answers. Yes, guys, this is on the directivity. See, two parameters are when it comes to the antennas, two parameters are extremely important. One is the directivity, other one is the effective aperture. So, for the transmitting antenna, directivity is a unique property, unique feature, isn't it? If you wanted to use the antenna for the effective communication, how do you position? We will position the antenna in the directivity direction. Why? Because we want to establish highly directional point-to-point communication in the satellite communication especially. So, for the transmitting antenna, what is more important is the directivity. For the receiving antenna, effective aperture. So, the receiving antenna should have a more effective aperture. It should be more visible to the incoming wave so that more reception happens. Okay, anyhow. So, here is a question, guys. So, find the maximum directivity. Maximum directivity, I do not know why they have used this word, because the directivity definition itself is a maximum. How the directivity is defined? The radiation intensity in the maximum direction by average radiation intensity. So, there is no need for that extra maximum, but it is that is how the question is framed. We need to go along with that. So, of an antenna whose power density is given by, so power density is given, where A naught is the peak value of the power density, theta is a usual spherical coordinate system, r and theta are the units. So, how do you find out the directivity? The directivity formula, D is equal to 4 pi divided by integral theta phi f of theta comma phi magnitude square sin theta d theta d phi. See, the power density proportional to the E magnitude square, which is proportional to the sin theta. What is this f of theta comma phi? It is a normalized radiation pattern. Fine. So, you can say that E magnitude is proportional to the square root of sin theta. So, this is we are least bothered about what is happening with the magnitude when it comes to the directivity. We are interested only in the normalized radiation pattern whose scale is from 0 to 1. So, check out what is the minimum value, it is a 0. maximum value is 1. So, this scale must be from 0 to 1. So, what is the normalized radiation pattern? F of theta, it is only function of theta, is square root of sin theta. So, bring this one and substitute here. So, what happens to the directivity D? D is equal to 4 pi divided by integral of theta phi, this one square. This one square is nothing but a sin theta. One more sin theta is there in the formula, d theta d phi. I will going to turn the page here. So, what happens to the directivity D? 4 pi divided by sin square theta d phi. Okay. So, let me call this as the integral I1, this is the integral I2. So, what is the integral I1 guys? So, it is sin square theta, this can be written as sin square theta d theta, this is 1 minus cos 2 theta by 2 into d theta, 1 by 2 into theta minus sin 2 theta by 2. So, where theta ranges from 0 to 5. Upper limit minus lower limit here. It is a 5, lower limit is 0. So, it is a pi by 2. Okay, guys. That is the integral I1. What is the integral I2 then? Integral I2 is d phi, which is phi. Phi limits are from 0 to 2 pi for the spherical coordinate system, full limits. So, I2 is equal to 2 pi. Okay. So, bring everything and substitute there. How much is the directivity? D is equal to 4 pi divided by, so it is a pi by 2 into 2 pi, which is nothing but 4 by pi. Directivity is a unitless thing. So, what is the answer here? Option A is the answer. Okay, guys. Yes. Okay, guys, let us move further. Let us proceed further. Here is the thing, one more question on antenna parameters. See how many questions are asked. How important antenna parameters are as expected. An antenna is fed with the 200 pi watts power. The efficiency of the antenna is 75%. See, the questions what I am discussing is the typical questions. Of course, there are some questions on the what is the cutoff frequency of the waveguide, what is the, if the electric field is given, what is the magnetic field, you can find out by using the intrinsic impedance. There is a direct questions on reflection coefficient, transmission coefficient, power reflection, power transmission, fiber optic cable, core and cladding, what is the critical angle, what is the numerical aperture, all these are formula based questions. So, instead of dealing with the regular questions, I have collected some typical questions from the previous ISRO paper, so that you will be exposed to something new, you will learn something new. That is my intention here. Fine, anyhow guys, so something a new model where you do not find such a models even in the GATE paper also. Very interesting question. Why? Because power radiation pattern is given, there is no such model in the GATE paper. If the radiation pattern of the antenna is given, P of theta comma phi, sin square theta, sin square phi, for theta ranging from 0 to phi and phi is from 0 to pi, elevation angle and 0 elsewhere, find the radiation intensity in the direction of maximum radiation. So, he is asking what is the radiation intensity in the maximum direction. So, the radiation intensity in the maximum direction is, we will get from the directivity, it is U max divided by U average. This is the definition of the directivity. Okay, it is asking what is this U max? U max divided by power radiated by 4 pi, average radiation intensity. Fine. So, the D is equal to U max 4 pi divided by WR. Is asking for the U max. Okay, let me turn the page here. So, what is the U max, guys? U max is equal to D into WR divided by 4 pi. But is the power radiated is given? No. How much is power supplied to the antenna is given, along with that efficiency is also given. So, this also can be written as D into efficiency into power which is fed with the antenna. So, eta is known, Wi is known, 4 pi is anyhow numerical. So, we need to find out the directivity D. So, how do you find out the directivity D? It is a 4 pi divided by integral f of theta comma phi. See, f of theta, I am going back to the previous question. F of theta is a normalized radiation pattern. It is related to the electric field and magnetic field. So, the square of the electric field is something related to the power. So, directly that is what the power radiation pattern is given in the question. Power radiation, the radiation pattern of the antenna. This is a power radiation pattern, P of theta comma phi. He must have mentioned in the question as a power radiation pattern, but he has not done that one. Instead of that, he has used that P notation. So, this is indicating the power radiation pattern. You can directly take up these things. So, there is no need to do the squaring one more side. They are all already in the square form. So, you can take up these values and substitute there. So, what are those values here? Sin square theta and then sin square phi and one more sin theta in the formula, d theta d phi. Clear, guys? So, separate out the variables here. It is a 4 pi divided by sin cube theta d theta and then sin square phi d phi. Let me call this as the integral I1. This is integral I2. So, there are different ways of finding the integral I1. I will strongly recommend you to go with a mathematical tool like a gamma function, which will going to save our time. Okay. Of course, this is not the session where I can discuss some mathematical techniques. That is your job. You need to improve your problem solving skill by doing more mathematics. Fine. So, but I will go in a different manner. Sin square theta can be written as, you can solve this one by using the sin 3 theta. Yes, or you can even solve in a much simpler way by using the gamma function, something like n into n minus 1 into n minus 2 and so on into pi by 2, something like that you will find in your mathematics. But I will going to do this one in other way. So, this can be done by 1 minus cos square theta into sin theta d theta. So, this is sin theta minus cos square theta into sin theta. See, you must be reasonably good at mathematics. Compared to all other engineering streams, electronics and communication engineering you will find the heavy mathematics. Yes, we will be dealing with the complex variables, we will be dealing with the differential equations, vector calculus, probability, random variable theory, linear algebra. You will find applications of all the mathematical tools in our engineering subjects. So, being an electronics and communication engineer, you must be reasonably good at mathematics. Remember this point. Okay. So, integration of this one is minus cos theta, differentiation of cos is sine, so minus sine, so it is cos to the power of 3 theta by t. So, here the theta is from, it is mentioned 0 to pi. Substitute upper limit minus lower limit, minus of minus, it is a 1, minus 1 by 3 minus 1 plus 1 by 3. So, cross check the algebra. So, it is 2 minus 2 by 3. So, it is 4 by 3. So, it is the integral I1. Fine. Let us try to find out the integral I2. What is the integral I2, guys? See, such a big question is asked. There is no shortcut, nothing. This mathematics you need to do. Fine. So there are such a typical questions are there in your previous papers. So there are some simple questions like the questions was asked to identify the Maxwell's equations. You will find even such questions also. I have not intentionally taken such questions. Fine. So this is 1 minus cos 2 phi by 2 into d phi. So it is 1 by 2 into phi minus sine 2 phi divided by 2. Phi is ranging from, it is also mentioned, the phi value is also from 0 to 5. Substitute upper limit minus lower limit, it is pi by 2. All the lower limits are 0. So you have got a I1 and I2. So what is this directivity D? It is 4 pi divided by I1. What is I1, guys? I1 is 4 by 3. I2 is pi by 2. It is a 6. Am I correct? So you have got a directivity. Bring everything and substitute here. You get U maxima. So what is the U maxima, guys? Directivity is 6. Am I correct with algebra? Eta. What is the efficiency? 0.75 into what is the power which is supplied to the antenna? 200 pi watts. It is 200 pi divided by 4 pi. So you are going to get U max. How much is the U max, guys? Check out this value, around some 225 watts per steradian. Am I correct with algebra? Yes, guys. Okay, guys. So 225, you can check out. Yes, I am correct. Okay, let us proceed further, guys. Yes, Anurag, what is your answer? Here is a one more question on the transmission lines. An RF signal is applied to 50 ohm lossless transmission line which is terminated in the load with the impedance ZL is equal to J50 ohms. The wavelength is 8 centimeters. Find the position of the voltage and current maxima. Voltage maxima, current maxima respectively nearest to the load measured from the load end. So to find out the V maxima or V minima, we need reflection coefficient. What is the reflection coefficient, guys? ZL minus Z0 by ZL plus Z0. It is J50 minus 50 divided by J50 plus 50. So which is 90 plus tan inverse of imaginary part by real part, which is 1, because this is in the second quadrant. Divided by tan inverse of imaginary part by real part, which is 90 degrees. 90 degrees is the angle. Just a second. So what is the magnitude of the reflection coefficient? Magnitude is not required, angle is required. So angle of reflection coefficient will represent with the phi L. So which is 90, because this is in the, this point is in the second quadrant. So 90 degrees plus tan inverse of imaginary part by real part divided by tan inverse of imaginary part by real part, it is pi by 2. Let me turn the page here. What is the condition for the V maxima? The total phase must be even multiples of pi. 2 beta L is equal to 2 m pi. For the first one, it is 0. So L is equal to phi L by 2 beta. So phi L is pi by 2. 2 into 2 pi by lambda, it is lambda by 8. So it is asking in the centimeters. What is the lambda, guys? Lambda is 8 centimeters. So it is 8 centimeters by 8, it is 1 centimeter. So this is the location of the first voltage maxima. 1 centimeter. So option A is the answer. From here itself you can decide. But for our practice, let us try to find out what is the location of the first current maxima. Current maxima in the sense, at the same point voltage minima is noticed. Fine. So let us try to find out what is the location of the voltage minima. V minima. V minima, guys. What is the condition? The total phase. Phi L minus 2 beta L must be odd multiples of phi. It is 2m plus 1 into phi. So for the first voltage minima or current maxima, or this is current minima. So m is 0. Fine. So it is phi L minus 2 beta phi. So what is this? It is a pi by 2 minus phi is equal to 2 beta L. So it is 2 into 2 pi by lambda is equal to pi by 2. So L is equal to, it is a minus, guys, minus or plus, just a second, yes, it is a minus. So it is a minus pi by 2 which is equal to 2 into 2 pi by lambda into L. So the L is equal to lambda minus lambda by 8. So it is minus 8 centimeters by 1. So L is equal to minus 1 centimeter. What does that mean? Nothing. So that means the origin is defined at the load side. So we are moving towards the generator. So if you move, that means, see here, you need to bring this one into the reality. So the minus distance has no meaning. How can you bring this one into the reality? We know that on the transmission line, you will find the repetition of the characteristics on the transmission line for every half wavelength. So you need to add up some half wavelength to that, so that you can bring that one into the reality. Fine. So this is the actual real value is minus 1 centimeter plus lambda by 2. Lambda by 2 is a mirror. So bring this one into the reality. So what is the lambda? 8 centimeters divided by 2. So it is a minus 1 centimeter plus 4 centimeters. So it is 3 centimeters. Clear, guys? So this is the location of the first Imax, 3 centimeters. Go back here. Yes, 3 centimeters. Option A is the answer. Okay. So let us proceed further. Let me turn the page here. Here is a question, guys. Direct. It is a simple question. The plane wave propagating through the dielectric has this one, or unit vectors, determine the polarization of the wave. See, the polarization is defined with respect to the electric field. So here the magnetic field is given, that too a uniform plane wave is traveling in the, it is a UPW, traveling in the positive x direction. So magnetic field is y, so the electric field is z. So it is z by hy is equal to eta. It is a minus here. So what is its corresponding electric field? Is a minus z. So polarization is always defined with respect to the electric field by default. So what is the answer here? It is a minus z cap. Linear minus z oriented polarization. So what is the answer here? Option B is the answer. Clear, guys? Fine. Here is a one more question. Yes. So the same model you will find in the gate paper also. So in the free space he said, okay, magnetic field is given. So he is asking what is the total power crossing through the square plate of side 10 centimeters, and where that plate is located, like this here, approximately he said. So how do you find out the power? First you need to find out the power density, P average. Then you need to perform the integration. So what is the P average, guys? It is eta naught into h magnitude square divided by 2, which is 120 pi into 0.1, just a second. So the power density will be in the direction of wave propagation. 120 pi divided by 2 into 0.1 whole square into x cap. Clear? So you need a W average. It is asking how much is the power crossing through that square region. So it is a P average into differential area. Remember, area direction is the normal direction. Then how do you find out the normal to the given plane? Normal is equal to gradient by its magnitude. So what is the gradient of this one, guys? The gradient of this one is, it is x cap plus 2 y cap. It is a x cap plus 2 y cap. Its magnitude is square root of 5. Bring everything and substitute there, perform the integration. So W average. Again, this is not a regular question, it is a typical question again. So it is P average. What is the P average here? This entire thing. So it is 60 pi divided by 100. X cap dot product with x cap plus 2 y cap divided by square root of 5 into differential area. So bring the constant, perform the dot product, bring the constant outside. So it is 60 pi divided by 100 into 1 by root 2, not root 2, it is root 5 into area. So what is this part is indicating? It is the area of that square region. So it is a 10 centimeters by 10 centimeters. So 10 into 10 into 10 to the power of minus 4. So can you evaluate this one? How much is this value? This algebra, you will going to find around some, you will get the answer in. Yes guys, what is the answer? 8.42 milli, I think. .42 milli, I think. Am I correct? No, 16.82 milli. No, check out. Come on guys, try to solve this one. So this 100 will go, it is a 6 by root 5. Yes, you can do this one. So it is this 100 will go, this will become 6 pi by root 5. Yes, so this is 18 divided by something 2.5, 18 divided by 2.5. So this will, it is around some D. Yes, D is the correct answer. So from the elimination you can find out that one, it is 8 point, because obviously answer will be less than 18. So it is from the elimination you can find out 8.42425 milliwatts. Okay, that is how you can eliminate from the options. Okay, let us have one more question. Here is a question, guys. Again, this is on the antenna parameters. An antenna with the efficiency of 90% has a maximum radiation intensity of 0.5 watt per steradian. Calculate the power gain of the antenna when the input power to the antenna is 0.4. So what is the power gain, guys? Power gain is equal to eta into directivity. What is eta given? Directivity. What is the definition of the directivity? I think definition of the directivity is U max divided by U average, which is power radiated by 4 pi. So 4 pi into U max. So which is efficiency into input power. So from here you can find out. So it is 4 pi into U max. What is the U max, guys? U max is given as a 0.5. Divided by efficiency is 0.9 into what is the power which is fed to the antenna? is input is 0.4. So you have everything and you can find out this. Again you must multiply with the efficiency, again one more time efficiency. So it is 0.9 into 4 pi into 0.5 divided by 0.9 into 0.4. So it is 4 pi into 0.5 divided by 0.4. So it is 4 pi into 5 divided by 4. So it is 5 into pi. 3.14. So it is 17.4. Am I correct? From the elimination, option B is answer. Okay guys, like this. So this session intention was to show you, was to expose you to the kind of questions, the type of question, the model of questions asked in your ISRO paper, so that when you are preparing you will focus on those topics. As I said earlier, as far as my subject is concerned, electromagnetic theory is concerned, so more questions will be on the applied electromagnetics. That means you will find very less questions on Maxwell's equations, theory on the Gauss law, theory on the Faraday's law, Maxwell's equations, continuity equation, potential, charge, all those. Instead of questions on those things, you will find more questions on the waveguides, transmission lines, fiber optic cables, antennas, antenna parameters and practical antennas, microwave antennas. Especially you will find repeatedly you will find the questions on microwave antennas. So when you are making a preparation, while you are during your preparation, focus on these things. And remember one more point, ISRO organization is conducting the paper, their intentions are very clear, their objective is very clear, that reflects in their question paper. Fine. So obviously they are using the wireless communication, microwave communication, radar technology, antennas. Yes. So and the questions will be inclined towards those topics. Okay guys, hope you would have enjoyed this lecture. So keep your preparation in that direction, what I have mentioned during my discussion. So all the best. May God bless you all. Thank you.